Good morning, good afternoon, good evening, wherever you are in the world, whether you're watching this live with me right now or whether you're watching the replay later in the day. Welcome to the second lecture in this series of 4 lectures about the correspondence, if you like, between the 7 Hermetic Laws from the Kybalion and electronics, particularly radio frequency electronics, or what we might call AC alternating current. Just to review what we talked about yesterday was the relationship between the frequency of the AC current, the wavelength, and the constant speed of light. So I just wanted to put that a slightly different way before we get into the new content for today. So basically what it means is that we can calculate the wavelength of a particular wave by taking the constant, which is the speed of light, which is 300 million meters per second, and dividing it by the frequency. Just changing the equation around, changing the order and sequence of the equation around. And so then, if we looked at, again, radio, and we looked at, when I was a kid, radio 2 was on 200 kilohertz. And when we do this particular equation here, 200 kilohertz comes out to having a wavelength of 1500 meters or 1.5 kilometers. So that wave, the distance between here and here for radio 2 on 200 kilohertz was 1.5 kilometers. Which is why in the day that was called long wave, right? And then as we go up in frequency, the one I mentioned to you yesterday, which was this one here, 30 megahertz comes out to 10 meters. So the distance between here and here is 10 meters, and 30 megahertz, or the 10 meter amateur band, would be called shortwave. Yep, because it's shorter. Then you got the kind of like the stations between 500 kilohertz and 1600 kilohertz were known as medium wave. But then, if we look at where we're going now with radio frequencies, particularly, we're getting to higher and higher and higher frequencies. So, a lot of the stuff that's coming out with this new phone system, mobile phone system, one of the highest frequencies is 60 gigahertz. Now 60 gigahertz is 60,000 megahertz. And if we work out the wavelength of that at 60 gigahertz, it comes out to 5 millimeters. So the distance here of this from here to here at 60 gigahertz is only 5 millimeters, like that kind of size, which is why these are called microwaves or millimeter waves. And the reason why, when we look at this tomorrow, that we're wanting to go, phone companies are wanting to go to higher and higher in frequencies, is that the higher the frequency, the greater the amount of data that we can put into that wave. We're going to look at how we put data into a wave tomorrow. Data or information into a wave. We'll look at that tomorrow. And the higher the frequency, then the greater bandwidth we can have, and therefore the greater data transfer rates we can have for a lot of the new applications that are coming out on our phones and tablets. Then they need more and more and more data. It needs to be a faster data link, which is why we need to use higher and higher frequencies. But this is the relationship between the different frequencies and the wavelength, just in review of what we talked about yesterday. Now, we also talked yesterday about the amplitude or volts being, how big the wave is. The higher the wave, or the deeper the dips, the greater the amplitude of the wave, and that's measured in volts. And I mentioned that the amount of push, if you like, behind this wave is the current is measured in amps. So a number of these equations are going to start to fit together as we go through more and more of the information over these days. But the relationship between the amplitude of the voltage and the current, or the ampage, is that this is what gives us the power. Yeah. So the power behind a wave, which we would measure in watts, is equal to the voltage times by the current. Yeah, the voltage being measured in volts, obviously, and the current being measured in amps. And those two multiplied gives you the power. So there's a way of thinking about this. If you thought about electricity as being water going through a pipe, then you've got the amount of water flowing through the pipe, the size of the pipe, and the flow rate. And so the more water there is and the faster it's flowing, the more power that water has. If you imagined it was a pipe and you've got a lot of water flowing through that pipe and it's flowing really, really fast and it's coming out of that pipe, and instead going into one of those old water mill wheels, then the more water there is to flow and the faster that's flowing, the more power it's got to be able to turn that wheel and generate energy, essentially. And that's what this is about. So if we took a certain amount of power, then the higher the voltage, the less the current, and the higher the current, the lower the voltage, to create the same amount of power. Now, where this becomes important in alternating current or in RF, which isn't there in direct current, is a process called induction. And this is a really important concept as we go through what we're talking about over these days. So what we've got is, if we think about a transformer, yeah. So like the things that you plug into the wall socket, which then feed your laptop or whatever it may be, then what we've got is we've got a coil like that, and we put in a AC current, at a particular voltage, and then we have another coil and we get an AC current out at a particular voltage. But there's no direct electrical connection between this side of the transformer and that side of the transformer. There is an electromagnetic connection, but no actual physical electrical connection. And what we say is that the current here is induced by the current here. So as the current flows through this coil of wire, then it creates an electromagnetic field. That electromagnetic field then induces a current at a particular voltage here. Yeah. And obviously this is coming in at a particular amount of power, which is the voltage times the current. Now, what most of the transformers that you'll be using in the home do, and by the way, This is how, for instance, I'm wearing my Apple Watch today, but this is how, if you've got an Apple Watch, you can actually charge your Apple Watch by putting on that little disc that you've got. You don't actually have to plug the Apple Watch into the to the wall socket, because in that little disc is a coil, and in your watch there is another coil, and so that induces a current in the coil in your watch, which then charges the battery in your watch, which is why you don't actually have to plug the battery in. That's where we're starting to use induction of current in modern day life. Now, what most of the transformers that you come across, because there's a certain thing here, is that there's a ratio between the number of turns in that coil and the number of turns in that coil. So if the turns in the coil on this side are the same as the turns in the coil, and by turn I mean, if you imagine wire being wrapped around my pen, the number of times that wire is wrapped around the pen is the number of turns. Yeah. So if these were the same number of turns in both sides, then the current and the voltage coming out the other side would be the same as going in. Yeah. But for instance, if we created one of these things, and another one here, and I'm just going to use these examples here, and there were 100 turns in that side and 10 turns in that side, and we put 240 volts, which is the mains voltage here in the UK. If you're in the US, then obviously it would be 120, and we put it in at a power of availability of 1 amp. Then the voltage here is going to be 24 volts, because we've got 1/10 of the number of turns. But technically, the power in is the same as the power out. Practically, there's going to be a little bit of loss between the two things, but technically there's no power loss. Power in equals power out. So since we've dropped the voltage down to 24 volts, then the amount of current will have to increase to equal the power. So now we've got 24 volts coming out at an ampage of 10 amps rather than 1 amp. Now that's the kind of transformers that we tend to have in the home for running computers, running laptops, running, you know, our various low voltage electrical appliances. Now, we mentioned Tesla yesterday, Nikola Tesla, and Tesla was looking at this in a slightly different way, because this is what's called a step-down transformer. What Tesla was experimenting with was step-up transformers. So, for instance, what he was doing is making a transformer, and let's say it's got 10 turns in that side, let's say in this side it had 10,000 turns, 1,000 times more. Now if we're here in the UK and we were to put that 240 volts in here, yep, at let's say again 1 amp. And what Tesla was doing as well was he was using high frequency AC. So high frequency AC in the UK, the frequency of the alternating current that comes out of our wall sockets is at 50 hertz, 240 volts. In the US, it's 110 volts at a slightly higher frequency, 60 hertz. But he was actually using radio frequency AC, very, very high frequency AC. And what this would do here is the voltage on this side would now be 240,000 volts. Very, very high voltage, but also at 1,000th of an amp. So very high voltage, but very low current, because the power in equals the power out. And you might have seen those demonstrations that he did, where he would literally be in this Faraday cage, which is a cage made of metal mesh, which prevents the electromagnetic field inside of the Faraday cage getting out, or electromagnetic radiation getting in from outside, almost like creating a electromagnetic operating theater, that like anything that was inside it can't get out, and anything that's outside it can't get in. And you might have seen those, it's photographs, it's not really on video, where he was in there with one of these things, which is called a Tesla coil, and he would be holding a metal bar and a metal rod in his hand, and there would be lightning coming to the end of this thing, you know, and he's holding on to, and he's creating lightning from the Tesla coil, but he's managing to be fine as far as that's concerned, even though he was taking such high voltage through his body, but the current was really, really low. Yeah, and you know, and he was creating not only 240,000 volts, because he would make massive ones of these things. He was able to create on this side of the coil literally millions of volts at very low ampage. And there's the reason for doing that is that when we've got very high voltage and very low ampage, and we transfer that power down a cable or a wire, then we get very, very low loss in the power, which is why you know, in the UK we see those high tension cables going across our landscape. They're taking electricity at around about 240,000 volts, but very low current, which means we can transfer that energy over a great distance without there being a great loss, because the greater the current going through a wire, the greater the loss will be. And then what we get then at the other end is one of these to step that 240,000 volts back down into 240 volts. And that's what we can do, and that's called a transformer, and it works by the process of induction. And you may have heard that what Tesla was working on is actually being able to transfer this very, very high voltage electricity through the air without physical cables. Well, that's actually what we're doing all of the time with radio, because this is the process that a radio transmitter and a radio receiver use. And that's what I'm going to be talking about tomorrow as we take this to the next stage of looking at radio devices. And the distance between here and the distance between here can literally be thousands of miles. This could be on one side of the planet, and that could be on the other side of the planet. And we can get that induction because of the wave transfer from one side to the other. So tomorrow what we're going to start looking at is what we call tuned circuits. A particular circuit that is tuned to resonate at a particular frequency. You know, if you're same age group as me, you might remember there used to be a TV advert in the days of cassettes, you know, if you remember cassettes, for a company called Maxell. And one of the adverts that they used to have was where they had an opera singer sing a particular note, which was the resonant frequency of a wine glass. And with that particular frequency and the resonance and the power and the energy in the opera singer's voice was capable, when it was tuned correctly, of smashing the glass. So that's the kind of things we're going to be looking at tomorrow, is tuned circuits, resonance, which is all related to correspondence. It's all related to vibration from the Kybalion point of view. And then we're going to look at how do we then go about putting information into the wave, so we can transfer information from one place to another without there being a physical connection. That's what we've got in store for you tomorrow. Again, usual place, it'll be on my profile, but also I share it into a number of groups if you want to watch it in the group. And we'll be here at the same time, 11 a.m. UTC, GMT, or as I mentioned, 1100 hours Zulu.